Excellent. Very good. So it's 5 p.m. European time. Good morning, everyone. Good afternoon. This is Mihajlo Raljic from RealPars. I'd like to welcome you joining the webinar. This is a webinar hosted by RealPars, RealPars, and WAGO. More to that in a minute. While we're waiting for the people to join, feel free to make yourself comfortable. I think it's going to be an interesting 50 to 55 minutes of webinar content and training with an interesting Q&A, hopefully at the end, but more to that in a second. Okay, good. So I suggest we start with the topic as such and do a quick agenda and round of introduction. Why don't we start with introduction? Shapour, you go first.
Yeah, sure. Hey, everyone. Good afternoon, good morning, wherever you are in the world. I'm Shapour, co-founder and CEO at RealPars. Hopefully, we're going to have a valuable 1 hour for you guys. We have worked hard to make sure that this 1 hour that we are spending together is going to be hopefully the most valuable 1 hour that you're spending this week. So let's hope for that.
Ken, you go next.
Hi everyone, my name is Ken Bourke. I'm a technical instructor with RealPars. Yeah, I'm looking forward to getting to know everybody in the chat and helping to answer any questions you guys might have on machine learning and industrial automation.
Brilliant. Louis.
Hi everyone, I'm Louis Moreau from Impulse, and I'm the Senior Developer Relation Engineer. So I just help you if you have any question. I would be more than happy to guide you. I will also do a small demo at the end of this webinar, so you can get more familiar with anomaly detection techniques.
Great. And last but not least, Jan.
Yeah, thank you. Hello from my side. I'm Jenke. I'm working at WAGO as a product and project manager for the topic analytics. Yeah, I will present you today the challenges in predictive maintenance. So I'm curious for the discussion and on the webinar.
Brilliant. Okay. After the introduction, a little bit of agenda. We will have essentially, I would say, 3 main blocks and 1 housekeeping slide and 1 Q&A section. The housekeeping I'll address in a second. Once we've done the housekeeping, I'll hand over to Shapour, who will do the basic outline of predictive maintenance and what it means and how it in principle works. After we've done that, Jan will take over to show from WAGO's perspective what they see as typical issues when doing predictive maintenance in an industrial context. And in the end, I will take over a little bit to explain what are the actual machine learning challenges we see, because we are a bit specific with what we do, but I'll address that in a second. And last but not least, we'll have the Q&A session, which we assume to be about 10 minutes, where you can, in the course of the webinar, already raise your questions, and please feel free to share them in the comments box down below. With that in mind, let me go to the housekeeping. It's quite simple. Stay engaged. We thought of an interesting and nice prize, I find. Questions which you raise and which we will be looking at and answering. The one who raises the best question in this context will win a prize of 3 months RealPars Pro membership, which is essentially exclusive access to the educational content, which RealPars is quite excellent at developing and working on. Stay online. We've had similar webinars in the past, and people were like, "Oh, can we get a certificate for attending? Because that is quite a nice topic, and we would like to kind of get that confirmed." And the answer is yes, you can get that, but please be with us and listen and engage with regards to the questions. Stay tuned. That is a relevant section, because this is kind of the kickoff of our series, and in the end you will have a chance to share with us what actually would you want to see in the next series of the webinars, because machine learning is a very wide field and you could do all sorts of things with it. The normal biggest and first entry point is usually anomaly detection, so we could do a very deep technical dive on how anomaly detection is actually done and why does it matter. The other option is dig deeper into industry-specific use cases, because we, as a company, have a vast exposure to all sorts of sensor, video, and audio cases. Then topic C is, once you start going down the route of machine learning, you might be interested in understanding, well, what kind of techniques are there, and when is what kind of technique appropriate? What are the pros and cons? And last but not least is an interesting question we often hear when we talk to customers, that the return on investment is an important question, especially with management, and that when you are a developer or a engineer and you're working with automation topics, that at some point you need to do at least some sort of basic assessment. You know, what is the return on investment if I implement this or that? And the point 4 is feedback. You will get a feedback email after this webinar, where we will highly appreciate your comments on where we can improve and what you liked and what you didn't like. Yeah, it's all equally fine to be shared with us. Without further ado, I'm handing over to Shapour to start and go deeper into what is actually predictive maintenance.
Yes, so hello again, everyone. Again, welcome to this live training session where we are going to discuss how predictive maintenance can help and also how machine learning can help with predictive maintenance for industrial applications. I just wanted to let you know that all the information that you're going to learn today is going to be applied to your day-to-day job immediately. So I think that this is going to be very useful information for you guys. I assume that you have already seen some of the videos that we have posted regarding predictive maintenance and how machine learning can be used for predictive maintenance. But just for those of you who are not familiar with the concept, we thought that it would be good for us to quickly review some basic information about predictive maintenance, and that is going to help you better understand what we are going to teach you next in this live training session. So like just starting with the basic, what is maintenance? So when you have a new device, that new device, it's problem-free right off the bat. And as you start using it, problems start to show up, and that's where you need to do maintenance, right? And we have 3 types of maintenance in basics. We have reactive maintenance, preventive maintenance, and also predictive maintenance. Reactive maintenance is where you wait until the device breaks down and then you perform the maintenance. Mihajlo, it would be great if you can go to next slide. Yeah, good. So yeah, reactive maintenance, you wait until the device breaks down and then you perform the maintenance. And that's why we like call it reactive, because we just wait and then react when the device gets to the point of failure. And next we have the preventive maintenance, which is when you try to perform maintenance long before it gets to the point of failure. If you Mihajlo, if you click, yeah, good. So you see that with preventive maintenance, we do we perform the maintenance long before it gets to the point of failure. But there is one main issue with preventive maintenance, and that is you waste device life that is still usable. So this is money you're leaving on the table. You're not using your device lifetime fully. And to solve this issue, we have predictive maintenance. With predictive maintenance, what you do is you just predict when the device fails and then schedule maintenance right before that. And with this type of maintenance, you can have less waste for your device life in general. Yeah, if you go to the next slide, Mihajlo. Yeah, good. So as you can see, if you go back to the previous slide, as you can see, the lifetime that we are that is wasted with predictive maintenance when you're applying predictive maintenance is way less than what we had for preventive maintenance. Now, predictive maintenance is such a buzzword these days, and everyone is talking about it. And there is a reason for that. Some data that we have shows that predictive maintenance, global market size by 2026 is going to be about $21 billion US. And this shows, and this indicates that how important predictive maintenance is and how important it is for us to learn about this topic. Now, there are some industries that are benefiting the most from this whole concept of predictive maintenance. And we have some of them here. If you go to the next slide, Mihajlo, we have automotive, aerospace, and energy. These industries are the industries that are benefiting the most from predictive maintenance. So this was just some basic information for you to get familiar with the concept of predictive maintenance. And I think this is going to help you better understand what we are going to present next by Jan, which is discussing about some real world challenges that these days we are facing in implementing predictive maintenance for real world industrial applications.
Great. While we are transitioning to Jan, one more comment from my side, which is this importance of predictive maintenance is especially in a period of potential economic downturn important, because it really makes sure that we have a longer remaining useful life. So that is really the key driver for anyone in manufacturing and production to keep their existing stock of machine as long as possible in operation. And that is why predictive maintenance is definitely not just a buzzword, but it's really a trend which is going to stay with us. With that in mind, why don't you, Jan, take over?
Sure. Okay, so I hope my screen is visible for everyone. So I'm very happy to present you the challenges with predictive maintenance. I mean, we are working all the time, not all the time, we also develop products, but most of the time we're still working in customer-specific projects where predictive maintenance is often a very hot topic. And just to that you maybe have an easier start than we had when we started with that, I would like to give you the most 5 challenges with predictive maintenance, which you may have to solve. So I will structure my talk in such a way that I will give you the challenge, I will describe this challenge, and in the next thing, I will always present on a real example, the most simple example that we had, how this challenge could be solved. And that should give you the idea how you could solve those challenges in your project. So challenge one. Challenge one is, of course, getting started. So how should you get started? When you want to solve a predictive maintenance problem the very first time, you should start with the most simple use case, which of course should be somehow profitable. Why should it be so simple? That makes, because you have to consider many further challenges, as you will see. So yeah, just really take your time for looking the most simple example. The next thing, it should be also, of course, profitable, because otherwise you can't convince your management that you should continue working on that. And next, build a powerful team. I will show you how we solve that on a real example. So in this example, it's from our own production, and it was a project where a colleague of me who's working in my team also was getting started, like you, probably. So in our production, we have injection molding machines, and there's a material distribution plant conveying the plastic granules to the different injection molding machines. Of course, in reality, more than 2 injection molding machines and maybe a few more colors, if you know our products. And you see the filter, it's very similar to your vacuum cleaner at home. At some time, you have to clean it. But when do you have to clean this filter? It's in this project, it was very similar to your vacuum cleaner. You probably don't know really when is the best point. You don't want to do that maintaining job too early, but if you do it too late, you're wasting energy and efficiency. And we need to build a team. And this is really the same for all predictive maintenance challenges. You should definitely include a process expert, because you somehow, as Shapour presented you want to measure the device health. And what is the device health? If you don't know, ask for a process expert and involve him or her to your team. You maybe are working in this project as a data scientist. You want to develop algorithms. This one definitely has to be included. And an automation engineer. If you want to include everything in your PLC logic, then you need to involve him if you are not it on your own. That's a perfect combination, and really work together in this project. Challenge 2. Of course, it's getting the right data. Predictive maintenance is all about data. So you need really to connect the relevant data sources, and which data sources are important. As we want to measure, as Shapour explained very well, the device health, we need to have all the data related to the device health. So you don't have a sensor probably who can directly measure the device health. So you discuss it with the experts for the process, what is the device health about, and then maybe you have to add some sensors or include existing sensors to have a good description of the device health. And if in reality, I mean, often you have a production process like ours or something else, and you of course can't measure the device health when the machine is already in a maintaining state, or if it's simply not working. So somehow you need to include often the machine state. So you have to somehow get information about the state of your control system. And next, of course, recording the relevant data. What is it in the real example of our very simple filter? So the device health, as you can imagine from your vacuum cleaner at home, the pressure depends on the amount of dust in the filter. So in this case, we measured the pressure in front of the filter and behind the filter. And this we did in this case with a controller, a PLC, which could be of WAGO, could be of any other company. And we did it in this case with the existing control system. We just this controller was controlling this whole plant, and we simply added this data. You can, of course, if it's not possible to enter this this existing control system, add a different device to get the relevant data, and you have to store them. So in our case, we used an industrial PC for that purpose. We put an Influx DB, it's a time series database. It's open source, and for visualizing the data, we use Grafana, which is also open source, that you don't have an investment for these things. Maybe it's a benefit in your first project. So, and then, as you see, I mean, here it's a sketch, but we see the differential pressure where no maintaining is done was increasing with the operating time. So probably as the time is increasing and this differential pressure is increasing, probably it's related to our device health. Challenge 3. Challenge 3 is probably new for most of you. It's about developing the algorithm. If you want to do it on your own, and I think at this part also, of course, Edge Impulse could help you. But if you want to do it on your own, you have many approaches for that. And you have to choose the right machine learning algorithm across many. So machine learning, many things exist also in the open source community, but there exist so many things that it's really hard and to know what approach may lead to the best result. Second, you have to calculate somehow the device health. And now we up to now talked only about the differential pressure in this example, and define a critical value, and you want to forecast when will this critical value be reached. And then predict, that when the device health reaches this critical value for scheduling predictive maintenance. In our example, we transformed the differential pressure in a measurement for the device health, and we only needed to extrapolate this data and define the critical value. And then here it's a straight line, and when this critical value is crossed with some amount of security, because the data is a bit noisy, we have perfect time for scheduled best time for the maintenance. And it was, of course, aligned to our control system. So we only use the data points when material was really convoyed. In our case, we were lucky. As I said, it's a very, very simple example. Sometimes real-world examples are not so easy, but this real-world example was so easy, and we were able to do this with a linear regression, but we adapted the loss function. We'll come across the loss function if you will dive deep into machine learning based on the weights based on the operating time. So points passed from the very past are not so important as points which are very new. Next challenge, challenge 4, is the rollout. Up to now, you recorded the data, you were developing your algorithm, and now, I mean, that can't be enough. You only solve the problem on your own computer, but you want to roll it out, you want to use it in your production now. So somehow you now need to deploy the machine learning. And what we did in our case is we also used an IPC, an edge computer for that purpose, which is powerful enough, definitely for such a thing. And you may have already some available. Yeah, put the algorithm there and connect it, of course, to your logic, which is in your control system. Next thing in rollout is make sure that your solution is now used by the employees. It can't be that you just develop the algorithm, say, okay, everything is working, I can do everything, but nobody is using it in the real production. So make that sure. How did we solve that? So we set up an infrastructure on our edge computer, receiving the data from the controller, putting them to the machine learning algorithm, putting it back, sending the maintenance order also to our existing maintenance system, because of course, probably you have already some maintenance system. So you need to really connect it there. Otherwise, you have, you're building a new maintenance system next to the existing one and nobody would use it. So this is a very important point, but in many companies, you will get the support for doing that. And talk to the machine operators and all the users which are involved to your solution. Ask them for feedback and motivate them for using them, and implement their feedback in your solution. Now, the last challenge. Challenge 5. Challenge 5 is just keep going. I mean, you have to go on. Now you solved your first predictive maintenance project, but in real world scenarios, it's probably only one piece of a whole chain. And when you did it, transfer the knowledge to your colleagues. You did something very good, talk about it, and spread your knowledge that not only you can solve the next predictive maintenance project, solve it with your colleagues and establish really predictive maintenance in your company. So yeah, that's all. So 5 challenges which you have to solve, and I give my best that you can solve them on your own the next time.
Perfect. Thank you, Jan, for this. I have seen some very interesting questions. They're coming in on a very regular frequency. Some very great questions. We are working along the way to respond to them. If we don't respond immediately, we will share the questions to all the participants who have been here and will give you the answers. So you should be seeing my screen now. Could you just confirm that briefly? Someone? Yeah.
Yes.
Brilliant. Okay, perfect. Good. So now you've had a bit of an introduction from Shapour on the basics of predictive maintenance. Jan has shown a very elaborate and very sophisticated way of doing that with a lot of hardware and other aspects which are relevant when you do that in what you need to keep in mind. Now we at EdgeImpulse are essentially helping people to develop their own machine learning models with their own data sets in a very fast and efficient way. And let me just so before we go into the details of what we do exactly, let me just briefly explain who we are. We are essentially a company based in the Netherlands and the US, and we develop a platform, which is our web-based platform where you can sign up literally after this webinar and start exploring how you actually work on machine learning. And the most important aspect, it has 3 things what you do not need to have. So number 1, you don't need to know anything about machine learning. Number 2, you don't need to be a data scientist. And number 3, you don't need to do programming. In order to develop your first model, everything is essentially a graphical user face, so you can really start exploring what do my data tell me, can I improve the quality, and so on and so forth. With that in mind, here is just a select group of companies who are working with us. These are OEMs, which are working from a standpoint of actual use cases they have, and that's what drives us. We're always very use case focused. On the other hand, we have a whole ecosystem of hardware providers, because one of the things what we are really enabling and what is really unique is that these models are very small. They are 3 to 5, maybe 15 kilobytes big, and they run on embedded systems, which means on a microcontroller, which, depending on the brand and the power, can cost less than $1. So that is really the power here, is that we are talking of an ability to deploy on very cheap devices, quite some sophisticated math, because that's what machine learning is all about. But I'll come to that in a second. So we help our customers to really build real world data sets. And I've already seen a very interesting question, which is how many data points do you need? Well, the answer by the English would be, how long is a piece of string? Which means it's very much use case dependent. There are some vision cases where 100 images are enough. There are some complex time series data points where you need 50,000 data points. So it's not very easy to answer the question. It's really use case specific. But what counts is we provide you an infrastructure which helps you to achieve that in a very structured and very efficient way, which is scalable. Yeah? Once you've done that and you have the data in a right ML ready format, you can then actually start working on your custom machine learning. And there you will be doing 3 things, which is ingesting the data, which means feeding the data into our infrastructure. Then you do something which sounds maybe complicated, but actually it isn't. And that is digital signal processing, which helps you to extract meaningful features, so meaningful information from your data, because data can be a lot, but information is what you really need, and these are the features. And these features are then passed on to machine learning algorithms, which are essentially predefined as per your input. So if you have sensor data, there's a certain class of ML algorithms applicable. More to that in a second. And last but not least, everything what we do is really meant to run on the edge, which means it's a microcontroller, a microprocessor like a Raspberry Pi, but everything above that as well. And this is where essentially we differentiate a little bit from WAGO. WAGO has the Atom PC and above, which is quite high power stuff, which is kind of a gateway or an edge device. We can run on much lower compute, which makes it possible to have it quite distributed. And that is, again, depending on the use case, what is better for you. Now, a little bit of a step back on how actually engineering and coding usually works. And I hope you see this crazy little animation here. These are our 2 founders. The blonde guy is Jan, who's our CTO, and the guy next to him is Zach Shelby, who is our CEO. And the video shows essentially one major aspect, which is motion. Now, how are you actually, if you go into the IT context, able to program something which is like a motion, right? How do you describe a motion? And that is a really lengthy process, because you need to define rules, x-axis, y-axis, and so on. And that is a lot of trial and error. So that's how, in the old days, rule-based engineering and coding has worked. Now, the breakthrough comes essentially from something else, which is the data-driven engineering approach, where you can say, you know what, I have the input and I have the output. So the input is my behavior, which is a certain vibration, for example. Yeah, it could be on a motor. And then I have the output is, okay, on Monday from 3 till 5, everything was fine, but from 5 until 6, there was something wrong. I don't know what it was, but it was wrong. So you can then correlate input and output and let the machine learning figure out what is the mathematical correlation between those two. And in the end, you have a solution which is mind-blowing, because you don't need to think about the math in between. The only thing what you need is collect enough input and enough output and share it with the platform So we will then figure out what is the best approach to distinguish these things. This is how the platform actually looks like, and it's really a very powerful tooling. You see here the red block, a white block, and a blue block. And that's all what you need to do, right? So in the red block, you ingest data. The white block is the digital signal processing relevant to your data. And then there is the actual machine learning part, which is what kind of algorithm or what kind of activity do you want to do? Do you want to classify things and say, I have error state, a loose screw on my motor, I have an electric stator winding issue, and I may have some other mechanical imbalance. Could be 3 different classes, right? So this is a possible request to solve as a problem. On top of that, you can add anomaly detection, which is tell me what is happening, which I haven't seen before. And that's especially tricky with time series data because that goes beyond usually our mental ability to process data. The really cool thing is we can handle sensor data, any sensor, pressure, temperature, current, voltage, you name it. Yeah? We work with audio as well, so you can use audio in the predictive maintenance context as listening into certain things. So we're working with a welding institute where we listen into the welding process, and we can say how good or bad the weld is simply by listening to that. Vision is a typical machine learning exercise where you can do visual inspection of product faults and figure out, is this a systematic problem or is it a random occurrence? And as mentioned earlier, it runs on microcontrollers, microprocessors, even on some cameras or computers, or the cloud, you can do that as well. Now, the key point why we do these things on the microcontrollers and microprocessors is that once the model is developed, which happens in our environment, you get a C++ library, which you can embed in your microcontroller. And then you don't need any internet connection anymore. Your device will be able to detect the phenomenon you've trained it on in the field and give you some sort of warning, whichever you kind of programmed it into. And therefore, it's really going to help you to understand what is happening out there. Now, here are the hurdles we actually see from customers. And we have this kind of 5 major topics we see actually when we speak to people. We are today focusing here on the 2 on the left, but let me just quickly go through those. It's like how to quantify and how to get management buy-in, which is a typical economic discussion. We can help here. We have the respective tooling for that. The use cases is, sometimes people come to us with use cases which are like, I want to do weather stations and I want to do micro weather modeling. It's impossible. You can't do either. You can't even do macro modeling with supercomputers. Yes, micro modeling is less than a huge area. It's a small area, but still, don't try to boil the ocean. It's not feasible for a microcontroller to do that. But then there are tons of predictive maintenance applications where it actually absolutely makes sense to go into the details there. Then we need to look at the feasibility from a technical standpoint. Then a technology, which means what kind of hardware is actually involved in this? Is this a brownfield? Do we have anything already available? Can we kind of retrofit stuff? So these are the things we see. And then these, I would say 2 here, availability of data and skills and everything around that of quality of data are the most critical kind of road barriers in the beginning. So this is why we are focusing today on those. So when we have this discussion with customers, then we have actually the problem that people say to us, you know what? I can't give you an anomaly. It's so rare, I don't see it. And I don't record things 24/7. So I can't even give you a big data set where you say, oh, on Thursday last week, I may have had an issue. That's one problem. The next one is building an actual predictive maintenance algorithm is, for many people, a total new field because they're like saying, look, I'm not a mathematician. I have no idea how to do that. And then the third part, which is really where the magic actually happens is automate and scale this process. What does that mean? That means when you have a model on a microcontroller or a gateway, for example, that's a starting point. The real deal is when you do the iterations. The iterations are when you manage to get data to flow and retrain the model and get it better and better over time. That's what we call active learning. So the solution for that is twofold. So the first is the software side, which is our platform, which I'm going to address in a minute. But there was also, I think, a question from Daniel around hardware. It's like, what kind of equipment do I need to buy? I'm working on a oil pipeline. What do I need to do? The ML brick is pretty much the answer to this. So I'll share that with you at the end. So when you look at the platform as such, then the data availability and the assessment of normal versus an anomaly is really the starting point. Now, what you see here is time series data, and you have the ability to distinguish what is a nominal state, which means the normal operating stage, versus idle. It's just an idle and it's not rotating at all, for example, right? So with that, you can immediately detect and distinguish those two within our tooling. And Louis will do a demo shortly, so I'll need to speed up a little bit, but he will show you how you do that. Now, the interesting part is that when you get new data into this, you all of a sudden realize, aha, here is a bunch of gray ones, and the algorithm has recognized that they belong together. So that is probably a nominal state already. Then some very new random but still cloudy points are appearing here, which are clearly something which has nothing to do with what we've seen before, right? So this is very likely a anomaly. And then there is something which a lot of people don't speak in reality, but it's very often the case. You see the odd one out. So this one in here, right? This one is blue down here, and this one is orange down here. Now, what is that? Very simple. These are junk samples. And that's the beauty of the tooling. You can literally, after you've ingested the data, in no time detect the quality of your data, because you can see this is weird. Let me click on that sample and inspect that, and you will figure out this is just mislabeled, either label it correctly or delete it. And then you have a higher quality data set for the ML exercise you're going to do. Oh, this is a bit messed up, that slide. So let me just sorry, I have to apologize for this one. Just going back, share screen. You should be seeing that now, right? Come on. Yes. So the first part, what we often see is anomaly detection, actually. The next one is classification, which is really distinguishing once you've detected an anomaly, like what is this kind of anomaly? And the last one is regression, which is essentially helping you to say, what is the remaining useful life of your equipment? So let me continue with this one here. I hope, yes. So how does that then actually work? So you see what we have here, which is very nicely depicted. That's the last of the three which we mentioned, which is automate and scale. We can really help you develop the right data set. Then we have the right data storage. Then we do the model development along the lines of typical machine learning exercises. But don't be scared. It's a guided process and it's very simple. And we've got 16-year-olds in high school working with the platform and getting quite some amazing results. So it is a very easy to use platform. And this one is a very powerful one, which I like a lot, which is essentially how you do the active learning, right? So you start with data collection, you do the design, you test Then you put that onto your edge device, which is a microcontroller and microprocessor. There you have an anomaly detection algorithm, which detects whatever is new you haven't seen before. This is stored in your cloud infra and then used to retrain. And then you can essentially, in an automated way, develop your custom firmware and update it on the device. So that's the last one from me. The reference design. So what have we done here? We've been speaking for quite some time with different customers, and they said to us at some point, why don't you come up with a reference design which is really helping to drive this predictive maintenance solution? So we have the so-called ML brick, which is a device you can mount, and it has the typical major sensor setups which you need for predictive maintenance. There's a strong focus on vibration, but we see also current, especially the motor current signature analysis is one application. But then audio, you can listen in also to high frequency vibrations, which are not the regular 50 hertz or 100 hertz, but 20 kilohertz and stuff like that. And temperature, obviously. And then it has all the respective connectivity you may need in order to extract the data. And it's really all a ready-to-go solution. It's a one-click data collection exercise. So it's really, really fast to get you kick-started in that process. So with that, I can stop sharing, and I hope we have some time left for Louis.
Yeah, I'm going to go quickly.
Yes.
Yeah, so I wanted to illustrate what Mihajlo what Mihajlo just shared. So basically, I hope you cannot see that like this thing on the bottom. Anyway, any machine learning project actually start with data. In this first case, I've collected some data on an industrial machine that has two modes. One is a nominal behavior. I'm listening for tiny vibrations, and one is idle. So there is actually nothing happening on the machine. For this, as I've seen a couple of questions of I need a lot of data to get started, etc. This is actually not true. You can start importing data from many different ways, and you can even use your mobile phone just to listen to tiny vibration or use audio. This actually works great if you want to demonstrate just the value of what you want to build. Then once you've got enough data, so here only two classes, I will create my impulse. Mihajlo said it right just before. So I've got my data on the one hand. I've got some spectral analysis. This is a DSP, so digital signal processing techniques that I'm going to use to, let's say, ease the raw signal and provide interesting features to the neural network. And then I've got two things. One is the classification. So in that case, my neural network will only learn to distinguish the nominal behavior and the idle behavior. And then on top of that, I want to add an anomaly detection. So if anything is too far away from that cluster, that classification, I will provide an anomaly score. And then on the output, I've got two things, which is idle and nominal. Here, as you can see, this is a nominal one. So it's also tiny vibrations, which really look like the idle one. But you will see that my neural network will actually be able to distinguish them all. I can generate the features, and I will be provided some insightful clusters. If I can distinguish at least several clusters, it means like my neural network will be very likely to learn easily. On top of that, now I've been training the neural network classifier. This is really easy with accelerometer movements. It's not rare to see 100% accuracy. And that does not mean that my model has been overfitted. It's just like the technique we're using provides usually good insights on accelerometer data. And then on top of that, I want to add to create an anomaly detection block. So for example, if I want to compare the nominal one, so I can see that this data is in this cluster. Same for the idle one. So it's more in that cluster. No, this is good, but how can I detect an anomaly? So I created a second project where on top of that, of my training data set, I've added a couple of anomalies in my test set here. And then if I'm going to have a look at the clusters, how they are split. Here I can see that I've got on the one side all the idle movements, second one all the nominal one, and then the anomaly. This is great, but usually when you have anomalies, you need to classify them, and you want to do something with the anomaly you detected. So here I've got a third project where I've got still the idle, nominal, and I've got two anomalies that I, let's say, collected enough data to actually train a neural network classifier on top of that. So one is anomaly heavy loaded, and then anomaly, it's a seal failure. What happens now is that I can still have a look at those and still have my my anomaly detection. So if one anomaly is not one of a heavy load or seal failure, it will just go over here. So I then collected some more which were unlabeled and actually fall into that cluster. So I can easily reset the label, which was anomaly unknown. And then the tool will help you to actually set the full all the one that are inside that cluster. So it's really a powerful tool to label as well your data. And then you can go over your active learning strategy, as Mihajlo said. Now this is great. I've managed to detect my anomalies, but then how can I predict the time of failure? Then I created a third project. Is when I fall into one known anomaly, I can monitor and I can label. For example, I have a device that records a machine, and every day you log you record some data, and at some point of failure, you just stop the time. And then you go over and you say, okay, this data was collected 4 days, 7 days, 8 days before the time of failure. So I just label all my data, and then I can use some regression techniques to actually predict the time of failure. And this is what you obtain. For example, if you're I've got a couple of well, this is going to be easier to use this. Let's say if, for example, I pass a new sample, so a new anomaly, and I want to know when the machine is going to fail, the results will be like it's very likely to fail in 3 days. So it might be time for you to change that piece. So this is how you use Edge Impulse Studio. It's really easy, and then you can deploy your model that you built using a lot of deployment options. You can easily test the model that you developed or that you built directly using our built-in firmware. But when you want to integrate that in a broader application, usually our customers and users just integrate the C++ library or any components that are suitable for their targets. I would be more than happy to take your questions directly in the Q&A. I think we are a bit late, so I'm just going to stop for now. And feel free to go on forum.edgeimpulse.com if you've got any questions. I spend most of my days over there, so I will be also happy to help you after this webinar. Thank you, everyone.
Brilliant. This is very engaged. I am very well pleased. We have 34 questions so far, of which 20 are answered and 14 are still open. It will be a tough draw for us for the best question because there are a lot of them out there. Do we, from the speaker side, have anything to add in the end? I think we have one more slide to share. Let me just do that. Yes, which is a little bit more resources for you guys when you venture out into this. But then I'll also give the stage a little bit to so hide the floating controls. You should be seeing my screen now, correct?
Correct.
Yes.
Okay.
Yes.
Great. Yeah, so Shapour, why don't you go first? Because you're first here on the list. You're going to be in Nuremberg, I think.
Yeah,
right?
sure. Well, Francis is going to be there. France Ribidoy with Tom. They're going to be there in SBS Nuremberg. So if anyone wants to visit and have a meeting, yeah, well, you can just get in contact, go to realpars.com or email us at hello@realpars.com. And feel free to check out our course library as well. And as we mentioned that we are going to give a prize to the best question here as well, 3 months of pro membership for RealPars.
Brilliant. Great. Then I'll go next. We are going to be actually as well at the SPSS in Nuremberg, but also at the Electronica in Munich. So if anyone is around in that region, feel free to reach out and get in touch with us. Anyone who has attended and who has contributed here will get a follow-up email so you know where you can get in touch with us. But support@edgeimpulse.com is the one way to get in touch, which is also an inbox. Louis is I think observing, so he will be seeing coming these questions in. The other aspect which we have in our platform, which is really nice, we have a lot of projects which are essentially public. What does that mean? That means the data sets in there, the techniques behind that are available to you, so you can experiment here, right? And that is really a great way to start your journey and really explore things. And we have got a partner site, which is Hackster. And Hackster, you can find the craziest things people are doing without tooling, from heart rate monitoring to predictive maintenance to speed radar. People have developed their own optical gauge measurement, with a microcontroller in a remote position, just reading out stuff where you can't change the gauge for whatever reason. So they're really not tons, but at least 300 different Hackster projects. So you can really dive into that. And if you have anything specific, reach out to myself, and then we'll take it from there. Jan.
Yeah, thank you. Also, we are at the SPS fair in Nuremberg. So I also saw someone who's in the audience was for Nuremberg. So I think a few of us will hopefully meet there. I will be there. And we will present a product there, which is made for the PLC programmers under you. And there you will have the chance with this product to implement analytic solutions, not only predictive maintenance, but really as in the we did in our project, combining the computing power. It's just that easy that you have to add some function blocks on our PLC, which allow you to, for example, do an anomaly detection on the PLC, or include your Python code, as one question was, or to do something predictive, and also which allows you to visualize and store your data when you want to analyze it. It really, this product comes from our experience and what we noticed in the project, and it's really meant for you as a PLC programmer to use and start your first analytics project or predictive maintenance project. So I'm hoping that I will see a few of the faces which I now can't see. Thank you very much.
Brilliant. Okay. One last kind of comment on this note here, because we're about to wrap up, and I'm quite impressed. We are very German. We are very in time, so it's 2 minutes to 7. Sorry, 2 minutes to 6 in Germany. We will share with everyone who has attended this webinar also the presentation here. We'll convert it to a PDF, and then you have it in your inbox. And as mentioned, if you have specific cases where WAGO can help you, please feel free to reach out to Jan. You will find the contact details in the email there. If you have specific EdgeImpulse questions, which are more broad in terms of applications, because we can do, as I said, sensor, audio, and vision, and it's a very low barrier to do things like ingesting. And we are having a very, very comprehensive set of documentation, so you can read up a lot yourself. But also we have Coursera courses which can be attended for edge machine learning. Plus, last but not least, Shapour and the RealPars team and our team will be working on an in-depth automation and predictive maintenance course, which will come probably early next year. But in between, we will have these webinars, so feel free to come in and join us again. And last but not least, really share with us in your feedback and in your follow-ups, what would you like to see as a next one. I had here mentioned deep dive anomaly detection, exemplary industrial use cases, or which machine learning for what use case, and last but not least, return on investment. I think with that in mind, I would like to thank everyone who has really worked hard here. Thank you, Jan. Thank you, Louis. Thank you, Shapour. Thank you, Louise, who is in the background organizing this from a logistical standpoint. Very great work. We will stick around and definitely follow up and answer all the questions in the chat. But a part of that, I wish everyone a nice rest of the day or a nice evening. Thank you.